Test, test, test. Perfect. Good. Okay. Okay. Then let's start. Thanks for joining. My name is Karsten. I work for Xtext, and I want to talk with you today about how to integrate expression languages into Xtext. Actually, most of the languages that I develop for my customers don't have to do with expressions. They're purely structural DSLs describing domain models, user interfaces, behavior, whatever. And there I don't need that. But sometimes you need to embed expressions, all the kinds of things like additions, multiplications, and so on. And that's unfortunately not that really trivial. But there's one thing that you could use. Whenever I used expressions in the past, I just said, okay, just go with Xbase. And this solves already some of the typical challenges like recursions in the grammar, like precedence of operators, associativity means in which direction is the code executed when we have expressions of the same precedence, and ambiguity in the grammar, and so on. And you could use, of course, Xbase in this in your language. That makes it easy. So you can just say, okay, I have a language that needs expressions, and then I derive from Xbase, and I get everything out of the box, and it's actually quite cool. This is bulletproof. It's shipped with Xtext. It's embeddable in your language, and it's strongly typed to Java. It has a code generator, the Xbase compiler that you could use to translate your DSL to executable Java code, and so that's normal the way I go. But sometimes it is not the right way. There are use cases where you just cannot use Xbase. One of my current projects is an example for that. It's an automotive vendor who has designed a DSL for expressing test procedures on cars. This has been developed, this DSL has been developed for 10 years. They have a compiler for that, and it's really evolved language. And they just use UltraEdit for editing these languages. And our task is now to build a better tooling, an IDE, for this language, which understands this language completely, and provides all the good things that we know from Xtext, like syntax highlighting, content assist, and so on. Therefore, there was no way to go with Xbase. We had to adopt this expression language. So the question is, how do I write such an expression language in Xtext? This is especially for beginners not that easy. But we could maybe learn something from Xbase, and that's what I want to talk with you about now. What can we learn from Xbase? How to build expression languages. Actually, if you look at Xbase, then it sounds really complicated on the first sight, but I want to show you some patterns that you can find in the Xbase grammar. And you can build your language with the same patterns. I will first show you the examples of Xbase, and then go in a little bit into the theory behind that. So first thing that we see when we see the Xbase grammar is it's not a generated meta model. So there's not the option generate the meta model for me with Xtext. The meta model is predefined. It's manually maintained. This gives you us much more influence on the structure of the AST, and that's important for ASTs for expressions. So usually you can start by generating the AST with Xtext, but at some point you will take control over this meta model and maintain it manually. So let's look at Xbase. That's excerpt of the grammar. Looks complicated, but let's look at some things. First thing that we see is every rule returns expression. So it returns always the same supertype. That's one pattern. Next thing that we see, that's an important thing. Each rule calls first the next rule with the next higher precedence. So this we see here. So the assignment delegates to the OR expression to the AND expression, and so on. This goes on and on and on through all kinds of expressions that you support in the language. Next thing that follows here is an optional part. That's always the same. You will find this all over the rules. An optional part which is introduced with a syntactic predicate. We talk about syntactic predicates in a minute. So this is the same pattern here, and followed by a so-called assigned action. This means here, at this part here, an object is created, and the thing that was passed before is assigned to a feature of a binary operation which is instantiated when it finds something that looks like a binary expression. And simple thing, operators are here just called with a data type rule. So this makes it easier to extend the number of operators for a certain rule. And in regards of Xbase, it's also that this makes it overridable. So when you derive from Xbase, you may have a different notion for the AND operator, like writing AND could be. So you could override this. But it's also better readable. At some place you will have something like primitive types. So string, number, boolean, something like this. So you have literal rules. And they will be collected by a single rule, which is again an expression. So these are the basic patterns that you find in Xbase. So let's get a little bit into the deep. Let's consider a simple sum operation. The first thing that is a problem with this kind of operations is, it could be extended 2 plus 3 plus 4, and this means there's some kind of recursion. So we could naively say, okay, an expression, some expression is expression plus expression, or it is just a number, but this has a problem. It is recursive, left recursive. And we know that Xtext is using Antler 3.2, which is an LL star parser and just cannot handle left recursion. So the typical way here to go is to refactor the grammar and do a left factoring. So a rule is left recursive when the first symbol here is a non-terminal and calling itself. So that's the left recursion here. It's not a problem to have a recursion on the right side. That's what Antler can handle. So let's the next thing that we could derive for sum expression is that, because it could say we have a rule called sum, which has a number on the left plus a number of the right side. And this part is of course optional, because we could just enter a number literal 1. What happens with the AST that is created for that? If we enter 1, this would lead to the fact that first the number is instantiated, and together with a sum object, and without a right option. If we make this with the plus operator, then things get even worse. We have a sum on the left with the number literal 2, and the right side is the sum without a right side. That's horrible. So fail. So let's have a look how we have to do create the sum rule. So we have an addition rule, and here we see this assigned action, and this is important here. And this the optional part is like before. So when we enter 1, then this will first delegate to the number rule. So this here is optional, completely optional, and actually we get just as a result of this parse tree just the literal. That's fine. Oh, this was not planned in my presentation. Have to. Okay, good. And if we press 2 plus 3, what happens? First, the parser encounters the 2, creates a 2 literal object. Nothing more. That's optional here. Now it finds that there's a plus, and this means that this part here is fulfilled. What it does now is it creates a sum object at this point of time when it encounters the plus. And then the current object, which is the number, will be taken and assigned to the left feature of the sum. And the right part is not optional anymore. So we have a sum object with a left and a right side. And this is the reason why we use these assigned actions here. So that's the right way to go. Let's make it a little bit more complicated. We don't only have sums, but different kind of expressions with different precedences. So in this case, we have an addition, multiplication, exponentation, and literals, and they are ordered in this priorities. Or a little bit more abstract, we have a chain of rules with different priorities. And the way to go there is, as we saw it in Xbase, first call the next rule. So this will be passed. If we enter some literal, it will follow the atomic rule, and it's just an atomic. But when we encounter something which looks like an expression of a certain priority, then we follow the path here in between and assign the object to some feature of that object here and do the rest of the rule, like plus, minus, whatever. And yeah, that's the common pattern here. So just delegation, and then here are the assigned rules. And this leads to the fact that this rule is the one with the highest priority, and this one with the lowest priority. We see here syntactic predicate. It's maybe also a feature that people are not totally convenient with. There are two options to express the syntactic predicate in an Xtext grammar. The most seen option is with the equals sign and greater, which means try to pass all the tokens that you see here, and when you when this can be passed, then follow this path. This thing here just looks at the first token. That's just a shortcut, but could be also the wrong shortcut for your grammar. I think this is the easiest way to know to remember what a syntactic predicate does. So you encapsulate or prepend a syntactic predicate for a certain pattern in your language, then the parser tries to parse that, and when it's successful with that, then it knows, okay, please follow this path. The typical example for that is the then else problem. So let's assume we have such a situation, if condition, then here another if condition, and with an else, but just with one else. The question is to which if belongs the else. This is the same expression, just with different format. So for the parser, it's the same. The usual semantics is that the else part would belong to this if expression. But you have to give the parser the hint that it has to follow this path. So this would be the way that you have to express that. So if you find the else, then the else part belongs to the if condition here. That's the proper way to use the syntactic predicate here. And we would create such a parse tree then. So then the else part would belong to the second if. Okay, that's already about the grammar itself. That's not everything that that it's important for expression languages. Another thing that is here important is a type system. Usually you have notion of different kind of types, like literals, strings, booleans, numbers, whatever. Yeah, therefore you have to implement such a type system. How do you do that? It's actually implementing a type system is, I can boil down that to answering 3 questions. For any expression, what is the type of that expression? It's easy for literal, it's the literal type. But if you go to a multiplication or so, then it belongs on the left and the right part of the expression. What is the actual type? The second question that you have to answer is, what is the expected type for that expression? So, for example, for a variable assignment, you expect that the expression is of the type that the variable is of. So that's the expected type. And if you have 2 types, then you have to answer, do they conform to each other? Is it okay if I have different types? Can I assign them? There's no real interface in the Xtext framework for providing a type system, except for in Xbase. But in Xtext core, we don't have an interface. But boiling down that to some interface methods, it's actually something like this that you would write in some kind of type computer. So give me the actual type of an expression, give me an expected type of the expression, and are they conformal to each other? Next thing that you would do is integrate this into validation rules. So you want to see if something is wrong, and you use expressions and they do not conform to each other. So you could write something like this: a type validator class extending your own DSL validator, either separate class or integrate this into your regular validator. This is the example where you just have a separate class for type checking. And yeah, then check any type on an expression, get the actual type, get the expected type, and if you can compute both, otherwise you can say, okay, I don't know what to do with that. If you can compute an expected and an actual type, ask the question, are they conformal to each other? And if not, then you have an error. Then you raise an error for that expression. Here's the way how you would integrate this extended type validator in your language in the runtime module. You need to have a single and eager binding for validators because the validator has to be registered in the eValidator registry when the injector is created immediately, and it must be a single. So that's also a hint when you want to decompose your validator classes and do not want to have a very long validator class. Just write another one and register it that way in your runtime module. So let's look at some examples for actual types and expected types. Simple expression, we have a number and a string literal, and we have an assignment with a plus operation. The actual type of the x is a number, because the variable x is a number. The actual type of this here is a string literal, so it's string. The actual type of this variable declaration is the type of the variable, so here also again string. Also this one here, the whole complete plus expression is of type string, because the left side is of type string, and we have the semantics that that we say, okay, if the left side is a string, then you can append something, and the result will again be a string. Also here we expect that the expression is of type string because the variable is of type string. Let's take a look at a slightly different example. The actual type of this plus operation will be a number, because x is the number, 1 is the number, so the result will be a number. But the expected type is string, so here we would have a type validation failure. The expected type is depending on the context, while the actual type is not depending on the context. You have to look where is this expression embedded in. If you make an assignment to a variable, then it is expected that the expression will be the type of the variable. If you assign something, then it must be, of course, the expected type is the type of the left side of the assignment. When you take the condition in an if clause, then the expected type is simple Boolean. You expect that the result can be evaluated to Boolean. Or if you have something like method calls, then you have to look up the method definition and say, okay, the third parameter is of type string. And this is actually one of the hardest parts in writing a type computer. But it's not that hard if you do proper testing, and that's crucial. You must develop expression languages with type systems in a test-driven way. So think about different scenarios, how your expressions look like, write a parser test, and also test the type computer. So given some expressions, what is the actual type that you expect at some situation, what is the expected type at some situation, and so you build up test by test by test, and then you can be safe that that your expression language will work. Yeah, and basically that's all of the mysteries in writing expression languages of the Xtext. So my recommendation is also if you have the situation that you want to embed an expression language in your Xtext grammar, take a look at Xbase. Learn from these patterns and apply these patterns. Then it's rather simple to write these things. You will find all the necessary rules that you will need, like multiplication, relational operations. unary expressions, atomics, type literals, whatever, you will find that already in Xbase. It's only that you may not can use Xbase. And then build this up one by one, following the patterns that I gave you here in this presentation, and cover this with tests, and then you're done. Okay, and I'm quite good in time, a little bit in front of time, but that's were the things that I wanted to tell you. Thank you very much, and I'm open for questions. Christian. That's a good question. And Lorenzo has a framework for that, for describing semantics in languages and describing type systems. Actually, I did not use it so far. Sorry for that. I think the answer is yeah, it may be worth a look and then integrate. But yeah, ask Lorenzo about that. Yeah, of course. Mm. Mm. Yeah, in my case is that I have the type system is actually mostly very primitive. They only have a set of primitive types, and that's all. When you have to implement a more complicated type system like Java, C, or so, then things may change substantially. Another question? Okay, of course. Yep. Okay. No, you don't. What? Wait a second. That's the slide. Um, exactly. Um, Actually, Lorenzo is right. It's not necessary that that you always use a predicate. Most of the times, Antler will tell you that already when you translate the grammar, if you need some disambiguation or not. In Xbase, the pattern is always use always a syntactic predicate. I had a situation where I actually needed a syntactic predicate. This was a situation where I had a block expression, so curly brackets, and within that, of course, a list of expressions. The problem was that there was also a concept which was a list literal, and this looked the same. Curly brackets followed by a comma-separated list of entries, which could be even, again, expressions. So in that case, I had to disambiguate this with the syntactic predicate. So you could try first without syntactic predicates, and yeah, when the Antler generator complains, then follow this pattern. Yeah. Oh, oops, sorry. Oh, where is it again? Sorry. Precedence, was it? Yeah. Yeah, he was. Yeah, that's a typo. Sorry for that. Good audience. Eagle eyes. Okay, then thank you very much. I'm here. One last. Yeah, with the operators. Um, the thing is, in Xbase, Xbase is a language which should be overridable. So you can redefine the operators, and then it's easy if it's just one rule that you have to override. There's no real necessity. It's just that it's better readable, that you say, okay, here could be the operator, and that could be this kind that list of terminals. Just matter of taste in this case. Okay, thank you. I'm at the booth, and later also at the reception. You can drink a beer with me and discuss this. Thank you very much.